going to apply them, though, is that we're going to apply them to what we call parent functions. We mentioned this the other day. We're going to use the absolute value function as an example. We have already looked at the absolute value function, so we're just going to do a really quick review of that very, very, very quickly. We're going to run through it. We've got the absolute value of x. The basic, just plain absolute value of x function looks like this. As a vertex at the origin, and each side has a slope of 1 or -1. The left side is -1, the right side is +1. So that's what our absolute value function looks like to start with. So we are going to look at, well, what happens when we put some different things in this function. It's not just the plain old absolute value of x. We've got other things involved. So I'm going to use Desmos if you want to graph it in Desmos as well, or if you want to graph it on your graphing calculator. Either way. So let's graph the original absolute value of x, and I need to zoom so that's a standard. Now, if you've never done this before, I suggest that you do this. Since we're comparing it, if you click the little wheel right here above where you put in your functions, you can change the color of any of the functions that you graph. Okay, you can change the color. So I'm going to make the original one black, so that I know what I'm doing when I'm comparing it. Okay. So then that first one that we're going to look at is the absolute value of x plus 2. Notice the plus 2 is inside of the absolute value bars. And I'm going to compare these two. The black one's the original. The blue one is the transformation. So y'all tell me, what has actually happened from the absolute value of x to the absolute value of x plus 2? Okay, shifted over. Which way? Left. Okay, in the negative direction. Absolutely. So we started here, we went left. How many units? 2. Okay, so do you think that has something to do with what's going on inside of our equation there? So we're just going to write in that box that we went left 2 units. What do you think is going to happen if we change that plus 2 to a minus 2? It's going to go right 2 units. Y'all already know. Good. It should be easy then. Okay. If I change the minus to a plus, or excuse me, the plus to a minus, now my new function is over here on the right with a vertex of 2, 0. That's something that I suggest that you do as well if you're trying to figure out what these transformations are doing. Find a key point in the graph. If there's a vertex, use the vertex. That makes it really easy. And actually compare the original point to the transformation point. And you can see very clearly that, yes, it does go right 2 units. All right, so I told you it does make a difference whether that 2 is inside the absolute value or outside the absolute value. So let's look at that really quickly. Let's take that and put it outside of the absolute value symbol. And we can see that this one went up 2 units. Number 3 goes up 2 units. So number 4, do we really have to graph it? No, it's going to go down 2 units. Okay, now that's all the adding and subtracting that we can deal with. Let's look at number 5 and number 6. We have 2 times the absolute value of x, and we have 1/2 times the absolute value of x. So let's put that 2 in front. Now notice, vertex didn't move. Okay, we didn't go up, down, we didn't go left, right. All that happened is our function, there are 2 ways to look at it. It either squished in horizontally or it stretched vertically. Okay, we're going to call this a vertical stretch. Okay, we're going to call this a vertical stretch by a factor of 2. Okay, vertical stretch by a factor of 2. Now, the way that I kind of explain it to help you kind of keep it straight in your head, because you can look at it both ways. Think about a balloon that has air in it, okay? If I take my hands on the side of the balloon and push the sides of the balloon together, what else is also going to happen to the balloon? If I push this way, it's going to go, that volume is going to be distributed more vertically. It's going to go up and it's going to go down. So that's what's happening with this function too, okay? If you look at it and you think that it's been squished in horizontally, well, what else has happened to it? It's gone up or stretched vertically. Okay, so let's change that 2 to a 1/2. 1/2. Okay, so we're black is the original, blue is the transformation. So this one has been, mathematically, we're going to call that compressed. We're not going to write the word squished, like I was saying a second ago. We're going to call that compressed. Vertically, kind of got my words backwards there, but vertical compression or compressed vertically by a factor of 1/2. Okay, it was compressed by a factor of 1/2. All right, last one. What happens if we put a negative in front of that absolute value? It flips it over. Okay, now let's be specific. Let's use some mathematical terminology here. We're going to call that a reflection. It reflects over the x-axis. Very good. It reflects over the x-axis. So while this is not the same thing as what you did in Math 2, there is a bit of a correlation here. There are things that are very similar. For example, the reflecting over the x-axis, the multiplying by the fraction, the adding, subtracting, they're similar ideas, okay? So if you got that in Math 2 and that makes sense, those are really good things